Thank you, Jason. Thank you all for being here. It's really a pleasure. And so as Jason's already intimated, I promised one supermassive black hole, but in fact, you get two. So this work that I'm going to be presenting tonight is really the product of an enormous effort from a very large number of people. And this is true of most of our scientific endeavors these days, not all, but many. And so tonight you're really going to be hearing a lot about the work from the Event Horizon Telescope. This includes members of my team. It includes Jason, who just introduced me, many of the members who are here at the workshop we're here participating in. And in particular, our current workshop is really thinking about plasmas and hot plasmas in these very extreme gravitating environments like the one you're seeing in this image right here from the Event Horizon Telescope. So I'm hoping to introduce you a little bit to these two black holes that we've managed to image with EHT, which is the affectionate term for the Event Horizon Telescope. You'll hear me call it EHT a lot. And I want to compare and contrast these two black holes. They are both strikingly similar and also quite different in some of their aspects, in particular in the environment in which they live. You're seeing this is our supermassive black hole, which we call Sagittarius A star. For those of you who are night sky observers, the reason it has this name is that you look in the direction of the constellation Sagittarius, look toward the center of our Milky Way galaxy. So next time you look at Sagittarius, you can think, aha, I am actually looking in the direction of the center of the Milky Way and in toward this amazing supermassive black hole that resides there. So I'll talk a little bit about Sagittarius A star. You can see this environment around the outside of the supermassive black hole, which is but a pinprick down here in this more zoomed out image. So we'll talk about that a little bit at the end of the lecture. And I really hope you'll collect up questions as we go along. I really love talking about this stuff, and I'm very happy to answer all variety of questions. Let's see if we can get the telescope here. Okay, so we're going to start with the telescope just to give you a very brief glimpse of what it looks like to collect data that allows you to image a supermassive black hole. Some of you have probably heard some about these supermassive black holes. It turns out the images we're making, that one you just saw, are teeny, 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 tiny fractions of the width of a human hair held at arm's length. They're actually totally amazing images, and it requires a world-sized telescope to collect data with that kind of spatial resolution, we call it, that kind of imaging precision. But as you can see here, when you look at our telescope, you will note right away it is not a single monolithic telescope the way you might imagine. It's not one dish. It's in fact an array of telescopes that are spread across the globe. I'll give you a little movie in a minute, introducing you to each of these observatories. You can see some of the observatories are collections of telescopes themselves. So in order to make this global scale observatory, you have to be able to link together a large number of observing facilities that are spread across our globe and even residing at our global poles. So make this into one telescope that gives us data that we can interpret to get these images. We use a technique called interferometry. So you can imagine this is the direction of our Milky Way's Galactic Center. And you can imagine these are two characteristic telescopes in our array. They receive light waves coming from some source of interest. But we want to know if two light rays are emitted at the same time, which wave is associated with which other wave, i.e. we have to correlate the signals between these two telescopes in order to know that we are taking an image of the same thing at the same time. And to do this, we connect these observatories through a correlator, which sounds really super fancy and actually looks like this. A correlator is just a really big computer. We generate petabytes of data. It's a huge amount of data to correlate and to be able to understand and to correctly associate signals from these different observatories. We need a lot of machine power. So that's the technique. And this is a brief introduction to these observatories. In EHT speak, the distance or the linkage between any two telescopes, which people often describe as sort of shaking hands, these are known as baselines. And so we use very long baseline interferometry to connect together these different observatories. And you can kind of imagine, if you think of the Earth as an entire telescope itself, that we actually only have a detector or a little mirror at each one of those spots where the telescope is located. And we need those linkages in order to be able to understand the data taken from one side of the globe and taken from the other side of the globe at the same time. But in fact, we don't have a complete plastering of telescopes across the globe, or you all would know that. And so we have some gaps in our data, and I'll come back to that a little bit later when we're talking about how we build these images in a little more detail. So those are the telescopes. But of course, to do this science, you have to have the people. So this is a picture of the EHT collaboration, actually only a subset of the EHT collaboration in Granada, Spain, just 3 weeks ago. So we managed to get together for the first time in many years. COVID has kept us working on Zoom, which has got its benefits and its disadvantages, but it's really nice to come together and all be able to operate in a single time zone for a week. I mean, you would not believe the number of phone calls at 4 a.m. that people get up for and contribute to in order to make this science happen. So a huge diversity of people work on this wide diversity of telescopes to bring us these really cool results. And of course, with each one of these individuals, you can see here's me over here. I probably look really jet lagged. I actually had a lot of travel trouble getting to Spain, so I made it for the photo. But each one of these different people comes at this problem with a different perspective. And I want to just share very briefly a little bit of my own background in the context of this big old collaboration. So I actually am I was raised in New Mexico, close here to all of you. And my first education was actually in classics, in philosophy, not in science. And I got very excited about astronomy reading this book right here, which is split into 2 volumes, but this is Newton's Principia. I can tell you what got me jazzed about this. I was a junior in college and university, and I was with a professor that was talking about 2 and 3 body problems and interactions. So gravity and how different bodies interact via gravity. And he started to tell us about how you can give a so-called gravity assist to a spacecraft. So you take a spacecraft, you launch it off the Earth with a rocket, you throw it toward another planet in the solar system, it whips around that planet, picks up a little bit of extra acceleration from the gravitational field of that planet, gets kicked out into the outer solar system, sort of like a engineering slingshot. And so I love this image. This image, if anybody loves like really cool visualizations of data, this is actually an enormous poster that I've only picked up a small subsection of. But what you can see here are the many, many, many different missions launched from our Earth and sent out into our solar system to study in situ the different planets that we live among. And what you can see here is that some of these orbits, you launch off the Earth and off you go to go study something far away, and that's that. But some of these orbits actually, you get launched off the Earth, you get whipped around Venus, you have another flyby around the Earth, and then you get slingshotted out into the outer solar system. I thought this was just spectacular. I was like, holy cow, that's for me. I want to be an astronomer. And so it took me a long time, many years to retrain into physics, but I really, really love this. And I want to point out one thing in this, and that I will actually connect this to black holes, believe it or not. So one thing I just want to point your eyes to, one of the missions that is shown here is Voyager 1, launched September 5th, 1977. This is one of the spacecraft that we've launched into the solar system that has traveled the furthest from the Earth. I'm going to use Voyager 1 to help orient you the size of these black holes we're talking about in just a little while. So you can see here that we do, even in spacecraft knowledge, even in this engineering field, ways of linking together these different bits of science. Okay, so how did I get from orbits in the inner solar system to black holes? Well, it turns out, here's your first black hole. I promised you 2 black holes. Here's the first one. This is the very first image released by the EHT in 2019. These data were collected in 2017. And this beautiful black hole is known as M87 star. This is in a cluster of galaxies pretty far away from our own Milky Way. It also has a beautiful native Hawaiian name, Poehi, which means the generative creation power of the darkness, which is a pretty awesome name for a black hole. It lives in the Virgo cluster. For those of you who are astronomy buffs, it's actually in the brightest galaxy in the center of this galaxy cluster. And so how does this link to those orbits on the last slide? So it turns out that what we're imaging, at least part of what we're imaging when we make these images with the Event Horizon Telescope, is actually photons undergoing orbits like those ones that you just saw in the inner solar system around the very strong gravity of a supermassive black hole. So these black holes are so strongly gravitating that they can actually redirect photons around them. And that's part of the reason that we see this amazing image of M87 in this case. And I'll show you a cool video of that in a minute. It's a simulation, but it's pretty neat to see how those photons might be behaving in this environment. This is our first black hole. This is our second black hole. So this one was just released earlier this year. This is the image of the supermassive black hole that lives at the heart of our Milky Way galaxy and was the black hole on my cover slide. This one, as I've mentioned already, we call Sagittarius A star, or Sag A star for short. And it's pretty amazing to be able to take a picture of our own galaxy's black hole. And in particular, because this black hole presents a lot of challenges. So I'm not going to spend a lot of time talking about the observational challenges, but I will talk a little bit about the characteristics of this black hole that make it really difficult to image. But you have to remember, when you think about looking into our Milky Way, you all have seen like kind of pictures of the Milky Way. Not really pictures, often they're reconstructions, but we have this sort of disky galaxy we live in, and we live in the muck. Like, we live in the stuff of the galaxy, in the plane of the galaxy. So if you want to look in toward the supermassive black hole, you have to actually look through all of the gunk of the galaxy. And so that makes actually imaging in our own galactic center really hard. In particular, it blocks out our view of optical photons. So most of the photons that are flooding this room are optical or infrared. Optical in particular is really successfully blocked by all of the dust and gas and stars and stuff in our Milky Way. We don't have a view of Sagittarius A star at those wavelengths. So we instead move out to long wavelengths, sub-millimeter, which manage to pass through all of the stuff of the galaxy more successfully, so we can receive those photons here on Earth, or higher energy photons like infrared, or some of the infrared and also X-ray photons, which allow us to see kind of at the other end of the electromagnetic spectrum. And I'll talk a little more about that later too. Okay, so this might be an audio challenge. I apologize if I burst all your ears. Hopefully not, though. I want to share with you another cool thing that we did for this recent data release. So when you're doing science, and the main sort of communication to the public about the science is an image, it leaves out a lot of the visually impaired or blind community. And so we've also worked really closely with some wonderful people at NASA and some scientists who themselves have lost their vision to make sonified soundscapes of these images as well. So I just want to share, I'll share two of these with you, but they're a pretty neat thing. But I'm hopefully not going to make too much feedback happen here. I'm going to stop talking, and I'm going to play for you this very cool sonification of Sagittarius A star. So if any of you like to go to bed with a sound maker, you can replace the waves with a supermassive black hole. How awesome is that? Okay, so let's get a little bit oriented about black holes. And please do share these. Actually, these are combined. They're available on NASA web pages. They're available on YouTube. And we also have 3D printed versions of the Galactic Center and of these black holes, which are also very nice for a tactile counterpart to this soundscape. But let's talk just a little bit about what we mean when we talk about a black hole and just how exotic these objects are. That very first black hole I showed you, M87 star, which is in the middle of the Virgo cluster's brightest galaxy, it contains 6.5 billion times the mass of our sun. These numbers are so big, astronomers frequently use relative units. That's why I'm giving you these measurements in terms of the mass of our sun. I could give it to you in grams, but like it's a little harder to build your intuition. So we often, even in all of our scientific publications, use these kind of relative units. We use them for distance a lot, we use them for mass a lot. So 6.5 billion, 6.5 times 10 to the 9 times the mass of our sun. So that's a lot of mass. But I promised to put this back in the context of that Voyager mission. At mass, this is this amazing, image of the supermassive black hole, and the XKCD Comics folks did us a favor and helped us put this into some physical scale. So you might be able to see here, there's a tiny little dot in the middle of that image. That's our sun. And the circle you see here is the orbit of Pluto around our sun, one of our most distant planets. And out here is roughly the scale of where that Voyager satellite, launched in 1977, has made it to in our solar system since the time it was launched. So despite the fact that this black hole has 6.5 billion times the mass of our sun, the scale of this image is only a little bit bigger than our solar system itself. So this is the thing you need to know about black holes. It's not just that they have a lot of mass, it's that they have a lot of mass in a tiny space. You might think our solar system is big, but imagine having 6.5 billion suns packed in here, right? Global warming is like no longer a concern you thought it was before. So this is a lot of mass packed into a very small amount of space. So just to bring that home a little bit more, here's another object that we know well. Here's our Earth. Our Earth is 3 millionths of the mass of our sun. We could make our Earth into a massive, not a very massive black hole, a very undermassive black hole, but we can make it into a black hole as well. All we have to do is take you, your uncle, your aunt, brother, all the trees, all the dogs, all the cats, all the mountains you've ever seen or known, all the oceans, the mantle, the core, and crush it into a sugar cube. So if you could take the mass that is present on our Earth and make it something the size of a rolling die or a sugar cube, that would become a black hole. What that means is that the gravity that is represented by that mass in that very small volume of space is so great that electromagnetic radiation, photons, sound waves, all the radiation we use for our GPS and everything, it's trapped in there. It basically is just stuck in orbit somewhere inside of that event horizon and can't get out. So it doesn't have to be 6.5 billion solar masses. It just has to be a lot of mass in a really small space. However, the two black holes I'm talking about today are very massive. This one is the more massive of the two, M87. And I want to make sure that you have Sagittarius A star with this same scale in your mind. So here's a zoom in of that image I showed you on the previous slide. The sun in this image would be right here in the center, Pluto's orbit, and here's Voyager 1 just reaching out to the very edge of that event horizon for that black hole. Sagittarius A star, though the two images when we show them side by side look very similar, is actually a less massive and much smaller black hole. So it has about 4 million, not billion, million times the mass of our sun. And if you were to put it on the same solar system scale and you had the sun's diameter as that white dot in the middle there, and Mercury's orbit plotted here, it turns out that that image of Sagittarius A star that I've showed you is something more like the scale of the orbit of Mercury. So here's 4.5 or 4.2 million solar masses packed into something that would fit actually within Mercury's orbit. Once again, a lot of mass in a very, very small amount of space. Okay. So this is just to bring home the fact that though we show you these two images, and from our perspective on Earth, images of these two black holes look about the same size. They are in fact not physically the same size. What we're doing here is we're taking the M87 star black hole and dragging it into the same distance as the Milky Way's galactic center, as our supermassive black hole. And you can see that indeed these images represent physical structures that are they're very different in scale. And the reason M87 and Sag A star look similar to us as observed from Earth is just that M87 star is super, super far away in the Virgo cluster. Okay, so this is the only sort of whatever table-y thing I will torture you with tonight. I just want you to see that these are these two black hole images. These two images are on the same projected scale on the sky for us. 50 micro arc seconds, so that's 10 to the minus 6 arc seconds, which is a measure of angle. And they look very similar in size in projection. And in fact, these are the only two supermassive black holes that we as the Event Horizon Telescope collaboration are able to get that image of the black hole event horizon, that dark patch in the middle. All the other supermassive black holes that we know of are either the kind of bright emission around the outside is too faint, or they're too far away for us to be able to make an image of them. So these are our two sweet spot targets for being able to make these images. I show you a few different characteristics just so you can see the ways in which they're the same and which they're different. So using scientific notation here, here's that 4 times 10 to the 6. And so this is the 4 million, and this is the 6.5 billion solar masses. Accretion rate is a measure of how much mass is flowing into the black hole, growing it. These are negative numbers here. So actually it's a very small amount of material falling in, but you can see that Sagittarius A star, our galaxy's supermassive black hole, is growing much more slowly. It has a lot less mass because this is a more negative number than this one. And there are a bunch of other different metrics and different ways in which they're the same and which they're different. I want to spend just a minute talking about the time scales on which they vary. These time scales end up being extremely important for us as observers trying to capture images of these black holes. These other properties are important for understanding the physics and the general relativity in the vicinity of the black hole. But as an observer, the time scales on which they change end up being very interesting. So this is a plot. I think this is the only one I have in here. This is the characteristic time scale versus black hole mass. Again, here is this low mass black hole and this higher mass black hole. And you can see these time scales reflected in this plot. The lower mass black hole varies on very short time scales, 4 minutes to 30 minutes. And this bigger mass black hole varies on time scales that are longer, 5 days to a month. So you imagine here I am, me and all my friends have gone out and we're trying to take a picture of a black hole. And my black hole over the course of the night changes around all the time. Right? This is like trying to take a picture of your kid as they're like swimming around at the bottom of a swimming pool. You've got all the gunk of the swimming pool and your kid won't stay still and you can't get a cute picture. So that's the way Sagittarius A star is. It's a very fickle, tricky object to image because of this time scale of variability. And I'm going to show you here now, these are these two images, once again on the same sort of rough, same projected scale on the sky. And next, I'm going to show you a simulation. So this is a general relativistic, magnetohydrodynamic, super schmancy simulation in the computer of what we think, if we could get perfect resolution on these black holes, what we think might be going on. And you're going to see how they change in time. So you can imagine taking an image of this black hole is a lot more tricky than taking an image of this black hole. Believe it or not, if you watch long enough, this one is actually changing. It's just changing really slowly. And that means that if I want to look over the course of a night, it's fine for me to average together all of the data I collect that night and make an image of the black hole. This one, I'm not assured that from 1/2 hour observation to the next, that black hole hasn't changed a little bit. And that makes building our images a little bit more difficult for Sagittarius A star and also very interesting, right? So this variability is characteristic of the black hole and actually pretty exciting, but it does make the imaging more challenging. Okay, so let's talk a bit more about these images. What are you actually seeing when you look at these images? I promised you a little video of photons orbiting a black hole. This is an animation of what happens as photons orbit a black hole. And I'm going to just let you watch through it once and have you notice that as this number picks up, n equals 0, n equals 1, the photons wiggle a little more. You're seeing an orbit and a half or 2 orbits or more interaction between that photon and the black hole. And those of you who are very keenly watching this video will notice that the ones that interact more with the black hole make a much sharper image, a much sharper ring. We call that the photon ring. And in just a second, all 3 of these different modes, these different numbers of interactions will all happen simultaneously. And you will see something like those simulated images that I just showed you before, where the photons that interact the least make the slightly more fuzzy, more probing of the environment just outside the event horizon. And the sharper ring here is tracing photons that have more gravitational interactions with the black hole. So this is a look at what we are aspiring to be able to do to test these interactions of photons of light and of charged particles in a very, very intensely gravitating regime, which we call strong gravity. And in fact, the meeting that we're having right here is called plasmas, all the hot charged particles and photons in strong gravity. So that's exactly what we are trying to understand is what are the diagnostics, what are the features we can pull out of these images, try to understand there are theories describing the interaction of matter and light in this very strongly gravitating environment are complete enough, whether they can really describe these images, or if we have tensions that we can build better theories to try to resolve. Okay, so this is just a snapshot showing you the same basic idea. You have photons having fewer interactions, more interactions, and more interactions. And what we observe when we observe these images is the composite of all of those different light paths as they reach toward us. Okay, so I want to talk just a little bit more now about this particular image, which is the most recent release, and help you understand two sides of the coin for understanding whether or not this image can be successful as a test of some of those models for general relativity. And the first thing I need to tell you is that this image is not the same as me taking a picture of Jason. It turns out that when the EHT tries to take a picture of Sagittarius A star, we're actually missing a lot of information. You remember how spread out those telescopes were on the Earth? I don't have a telescope at every point on the Earth. It's sort of like I can see like one check on Jason's shirt and maybe a little bit of his shoelace, and I have to reconstruct my image of Jason by using all of the data that I can bring to bear on the problem. But there's missing data, and all I can do is take my best guess at filling in that data. And that means I can realize a bunch of different images, all of which are faithful to the data, that use something slightly different in the reconstruction. And so this is what happens when we try to make these images of Sagittarius A star. I'm going to show you what's flying, swirling around on the screen right now are a whole bunch of different realizations, all of which are faithful to our data, but which fill in that missing data slightly differently in our computers, in our created images. And so when I show you that images of Sag A star, what I'm showing you is a composite, sort of a representation of all of that data and all of those possibilities kind of simultaneously. Of course, we're smart and you're smart, and we can use both human intelligence and artificial intelligence to classify these different types of images we've made, these different realizations of the image, into some sort of meta data sets. When I do that, I get sort of 4 classes of reconstructed images. You can see they all kind of look like that image of Sag A star that I showed you, but they have slight differences. You know, maybe this little blob is a bit brighter, instead that blob is a little brighter. This one doesn't look quite so ring-like. And then I can use my reconstructed images to try to figure out how important each one of these different images is, how much weight I give each piece of that reconstruction. And that's actually what we do. We used all of the members of the collaboration to classify images. We also used machines to try to classify these images. And we created these 4 sort of subsets. And these are the sort of relative weights, the relative importances. So this one you can see is pretty important. This one here, which is represented by this pink histogram, is probably the most important, the most common image class that we get when we do this reconstruction. This one a little less so, this one less so. And so then I can weight these a little bit and reconstruct a sort of an average image of Sagittarius A star to show you as the sort of best, most faithful representation of what our data would look like if we could walk closer to the black hole or see it with more perfect telescope observations. This is the second thing we do. So that's about the imaging itself. Let me actually just go back for 1 second and say the next thing that we do now is we want to compare this image. We feel pretty good about our image. We've tried a lot of things. We've really hammered on that data, and we have the best possible image we think we can get. Now we want to use it to test our theories, our general relativistic magnetohydrodynamic models, Sgr MHD models. So what we do is we make a suite of simulated images, all of which represent different physical realities in the vicinity of the black hole. And we're going to use our image, our Sag A star image, to compare to this library of simulated models. And the models that don't match, we can reject. And so we're going to go through a rejection process, and we're going to remove models from this library because they don't make a good kind of comparison to the data, the ground truth of these observations. What you're going to see here is models being rejected. This is a little simulation it will play. You'll see models being rejected based on the EHT data, a couple different features of the EHT data. Turns out we also look with other telescopes, not only the EHT, but telescopes in space, other telescopes on the ground. We can use those to reject some of the models as well. And then we can also use other kind of radio measurements to try to reject some of the models. So we bring all of our tools to bear, and we try to, oh, sorry about that. And we try to figure out which one of these models is the best approximation of our data. So you'll see in just a second, the first thing that's going to pop up on the screen here is a couple of models disappearing in this corner because they don't match the size of the EHT image. They're just not a faithful match. And you can reject a whole lot more because they don't match the shape of the EHT image. Spectrum is shorthand for all those other different data sets, the ones from space and other observatories on the ground. This is lower frequency, so longer radio waves. And you can see we've gone from this huge library of models, just a couple that seem like they can actually match with our data pretty well. And using this comparison, we can actually try to see whether or not our theories are robust and are capable of really giving us something that matches our data well, whether or not we really understand what's happening in this strong gravity environment. Okay, so this is my last topic, and then we'll switch to questions, and you all can ask me things you're curious about. I want to just spend one more minute talking about, or a few more minutes, talking about all these other telescopes that we use alongside the Event Horizon Telescope. So you can see here that it's quite a different, quite a spectacular array. Many of them are sort of ground-based observatories linked together like the EHT, but others of them are actually observatories in space or in different settings on the ground. You can see Hubble, many of you might know, Chandra. There are quite a few other observatories that create some of the spectacular data sets that we've gotten kind of spoiled with in astrophysics. So what do these telescopes tell us? So it turns out that we're really interested in these supermassive black holes for their tests of basic fundamental physics. But of course, each one of them is placed into an individual and unique environment, as we all are as people, for example. And it turns out these little tiny black holes sit down in the centers of galaxies. Maybe they have accretion disks, interesting inflows and outflows of mass. Maybe they have big relativistic jets. What we'd like is to link together our observations down very close to the event horizon to some of these gross properties, these larger scale properties that we can observe more easily in a larger number of galaxies, and try to build up our sort of suite of knowledge that goes all the way from that teeny tiny scale of the event horizon out to these larger scales that we've been studying for decades as astronomers. So this is a really cool zoom out now. This is the M87 black hole, which it turns out has a truly spectacular jet. And what you're going to see as we zoom out, you can see a little size scale clicking by. We're going to change wavelengths, and you'll also see this box expand out from a fraction of a light year. We're looking at something a little larger than a light year now, and 10 light years. As it zooms out, you see on each one of these scales, this jet becomes more and more and more prominent. So it turns out that this M87 black hole, while very, very interesting at these very small scales, is driving an enormous amount of energy out across 7 orders of magnitude in its own galaxy. We're out here at 10,000 light years. Remember, we started at a fraction of a light year. All of this is real data showing us what's going on enormously large scales within this galaxy, linking that black hole to this very kind of amazing large scale structure, which is probably controlled by magnetic fields and maybe by black hole spin and other properties, even very close to the supermassive black hole itself. So this is some of the power that we can get from using multiple different wavelengths. Data from different observatories is starting to see some of this larger scale environment that the black hole is embedded in. That's M87. This is a still of that suite of observations, once again, just so that your mind isn't trying to track all at the same time. Here's our EHT image. Once again, this is 0.013 light years, so a very small scale. And we can go all the way out to 1,300 light years, and even out to 13,000 light years by using observatories across the electromagnetic spectrum. So this is a very powerful multi-wavelength. Jason said I was a multi-wavelength astronomer. This is true. I actually love to take data from as many observatories as my colleagues will let me get my hands on to try to understand what's happening across all of these different physical scales. Okay, next up, we want to look at a similar kind of thing for Sagittarius A star. And I hope you notice as we go through these zoom ins to the center of our own Milky Way, I hope you notice that this environment looks really different. So I'm going to show you 2 different movies. I might come back and start this one again. This one started with a sort of an optical picture, and then it's been only long wavelengths similar to the ones we observe with the EHT, so radio and submillimeter wavelengths. And we've zoomed in using real data. Everything I've showed you in these movies, these last couple of movies, is all real data from real observatories, going from those incredible large scales, looking in toward our own galactic center, zooming all the way into the supermassive black hole. I want to go back and just play this one more time for you in part because I want you to like really focus on one particular thing, which I just think is cool. And that is at fairly large scales, this beautiful image that's just about to resolve for you is from the Meerkat Observatory. And all of this cool looking weird structure is guided, we think, by magnetic fields that are on galactic scales, huge tubes of plasma trapped within magnetic substructures in the galaxy. And then we've passed through all sorts of other phenomenology to get in toward our supermassive black hole. Okay, so there's more. This is the same idea. We're now using, again, real data, but we're not using only long wavelength data. So we're starting here with optical data. As I told you, we can't really look, all this dust and gas and stuff in the Galactic Center is blocking our view of optical photons. We'll shift in just a minute the infrared and X-ray observations. And so first, what you're seeing here is X-ray observations of this region very close to Sagittarius A. Sorry for the jerky video. And you can see here 10 light years. Remember that video we saw from before? This is X-rays. That's a 1,000,000 Kelvin plasma. There's a big bubble of hot X-ray gas around Sagittarius A star. Embedded inside that bubble of gas are stars, stars more massive than our sun, but just regular old stars. And these stars, these two amazing teams, which I'll give a shout out to in a minute, have been monitored for over 20 years orbiting around the supermassive black hole. It's actually these orbits, these stellar orbits that allow us to know the mass of our supermassive black hole very accurately. They're basically just test particles orbiting around a very massive object in the center of the galaxy. A beautiful new instrument called the Gravity is now getting really close there, and you were seeing some of the closest orbits we know of. And you have to go in still 3 or 4 more orders of magnitude to get to that Event Horizon Telescope image. So there are your grand tours. These are pretty fantastic observations. I hope you will agree. To be able to see across all of these orders of magnitude in toward these supermassive black holes is really spectacular. And I want to emphasize again that you're really seeing different environments. Sagittarius A star, as far as we can tell, doesn't have a spectacular jet like M87. So even though these two black holes seem to operate in this strong gravity regime, photons seem to orbit around them in ways that we can try to predict and mostly expect. Environments, when you take just a little bit of a step back, are really different in these different galaxies, and the feeding and the overall interactions of the black holes are quite different. All right, so I'm almost done, and I just want to share, I have one more soundscape. Again, I'm going to close my mouth and just show you one more really cool sonic version of what this image looks like in the Galactic Center. So Sagittarius A star is buried down in here in this hot X-ray plasma. The kind of orangey colors you're seeing are infrared light, that's stars. The blue colors are X-ray gas, really, really hot plasma in the Galactic Center. And the kind of purpley colors are radio plasmas, ones that are emitting at radio wavelengths. And our sonification expert actually has 3 different sounds associated with those 3 different wavelengths of data. So if you're really excited about this, you want to learn more, you can find them on YouTube, but I'm just going to play the composite here for you. Kind of pick up the little, mute this, you kind of pick up the little guitar picky sound that's going with the orange stars. So this is really intended to help bring people of low vision into this cool discovery space. But I have to say, as an astronomer, I had never really noticed how dark it is over here until I listened to this sonification. I was like, wow, there was a lot of action over here, and there was really not a lot of action over here. I think this is probably just a lot more obscuration, more dust and gas on this side of the black hole than over on this side. But sometimes when you use a different way of trying to sense your data, you learn or observe new things about it that you hadn't before. I just want to look forward into the future just a little bit. I hope some of you got excited about the amazing new images that came out just last week from the James Webb Space Telescope. This is our latest great observatory in space. This is Stefan's quintet, which is 5 galaxies that are interacting with one another. And you're seeing a side-by-side comparison of the Hubble Space Telescope image and the James Webb Space Telescope image, really pulling out slightly different wavelengths, but also showing off this incredible, really beautiful precision with which James Webb can see stars and gas and dust. And I want to link this to the EHT a little bit by pointing out this particular galaxy that's up at the top of the image here. And to let you know that inside of that galaxy is what we call an active galactic nucleus. That's an actively growing supermassive black hole, a little bit like the ones that I've showed you today, but actually probably growing even a little bit more spectacularly. And James Webb has a few modes. It can take images, but it can also help us pull out different layers of this image and different ions that are being excited in this galactic outflow. And you can see here in these little cutouts, there's a bit of an outflow. There's a bit of one of those jets. And so what we aspire to do is to use the EHT and James Webb. So we have time coming up on the James Webb Space Telescope to look toward the Galactic Center, to look at our Milky Way's black hole, Sagittarius A star, at the same time that the EHT is observing, and try to understand what's happening in the surrounds, a little bit more about what's going on in that galactic environment. The James Webb Space Telescope will never have the same resolution to see the black hole image that the Event Horizon Telescope does. James Webb is not as big as our globe, but it's going to give us some interesting additional information. Let's see. Oh, I wanted to make one other point, and that is, you remember in the Sag A star zoom in when we could see those stars orbiting around the black hole? So far, Sagittarius A star is one of the few environments where we've been able to measure those orbits. The James Webb Space Telescope might be able to pick out stars like that orbiting around M87, other black hole. So there's a lot of different, very interesting kind of cross checks and new data that we can bring in to try to understand these black holes and their environments. All right, so in case I haven't shared my enthusiasm about black holes with you yet, let me also just say that black holes have been all over the news for the last many years. Of course, I think you've probably seen other lectures about the discovery of gravitational waves or the detection of gravitational waves from merging black holes. One of my favorite quotes of all time from Ray Weiss, who's one of my favorite scientists of all time, every day is an interesting day. I think that is true, certainly in our field. And then of course, this really exciting Nobel Prize for our field to Andrea Getz and Reinhard Genzel alongside Roger Penrose. These are these two teams that have been tracing out these stellar orbits in the Galactic Center. Stars, these are kind of colorified for you, but these are real data of stars orbiting around the supermassive black hole. And the star is just there to guide your eye. But that's the sight of the black hole guiding the orbits of these really big, massive stars in the Galactic Center. So these teams, Reinhard Genzel and Andrea Getz, have been doing this work for over 20 years, really just groundbreaking effort to verify the existence of a black hole in the Galactic Center and lay the groundwork for the Event Horizon Telescope to get in there and try to figure out whether or not we could make that image I shared with you today. And with that, I'll just say thank you.
For the wonderful lecture visuals and really spectacular. Questions from the audience?
I always wondered where the brightness came from. What activates the photons or whatever they are to give off such massive amounts of light?
Yeah, so it's very hot. Remember, so when you think a little bit, you can always, one of our classic examples or visualizations is a bowling ball on a trampoline, right? So we think that black holes, these really dense objects, kind of warp space-time. When you do that, you pull things down very deep into a gravitational potential well, which they get a lot of energy. So they're basically very hot charged particles in a plasma just outside the event horizon of the black hole. So once you've crossed into the event horizon, photons don't come out anymore. The images that we're seeing is stuff that sits just outside of that point of no return. And because that stuff has fallen very deep down into a gravitational potential well, it's excited and heated to very high temperatures. So that's what's creating that hot plasma just outside the event horizon. Does that answer your question? Yeah. Yeah, yes. Oh, we'll go here and then here. We're going to go youth first and then we'll go, yeah.
How does a black hole grow?
That's a super good question. So we call this process. Oh, I'm sorry. I'll repeat the question. Thank you for alerting me. How does a black hole grow? So astronomers call this accretion, but you can just think about it like eating dinner. Basically, you just take stuff and you throw it in there. It gets bigger. But that's the simple answer. It turns out that we don't really know. So there's a couple of sneaky things I didn't tell you guys about today. And that is that The stuff that's outside the black hole, it's not always falling in. Sometimes it's actually being driven back out. So you remember those big bright jets I showed you in M87? That's one indication that mass and energy get pushed back away from the black hole. But we sometimes have winds. It looks actually like a lot of the mass that's trying to get into our black hole, Sagittarius A star, not successfully getting in there. It's actually being pushed back out, sometimes from photons slamming into the particles and actually giving them a little bit of a loft, sometimes magnetic structures. There are a lot of different processes that might push that mass back out. But so feeding a supermassive black hole is actually surprisingly tricky. In Sagittarius A star's case, the plasma around the black hole is very hot and kind of puffed up. And that makes it even harder for it to get inside. In some cases, the very brightest growing black holes we see in the universe, which we can see out to the way, way far distances away, those ones have a lot more mass flowing in. And if you have a lot of mass flowing in, it kind of can help guide that mass a little more successfully across the event horizon and into the black hole. But those ones that are growing rapidly, we call sometimes active galactic nuclei, and the most bright ones we call quasars. And quasars we can see out very close to the edges of the observable universe, not all the way there, but pretty far. So they're really bright when they're growing a lot. Turns out, just to make one more caveat, so not only does mass flow in, sometimes mass gets shoved back out. The other caveat is that we don't actually really know how you make supermassive black holes that are as big as they are in the age of the universe. Turns out it's so hard to get the mass in that we can't figure out how to shove it in there fast enough to make those things as big as they are. So this is a kind of an open question. We think you can build small black holes by exploding stars, but we can't build from a small black hole into a supermassive black hole fast enough to have really big ones in the present day. So something else has got to give. So there's still a lot of really interesting research and understanding how they grow and what the different mechanisms are, and whether there are two totally different classes, whether you can grow one from the other. Can you just smash a bunch of them together? Like, how does that work? And there's a lot of different stuff. I have a very good James Webb talk. I think I have 1, 2, and then maybe I saw another one. Oh my God, so many. Okay, we'll start here.
Maybe my answer is part of my question, but I was going to ask, why do some black holes have the jets coming out and some don't?
Yes, the question is, why do some black holes have jets and other black holes don't? Another profound question. We were discussing this yesterday in one of our discussions. So probably it has something to do with the spin of the black hole, and something to do with how magnetized the medium is around the black hole. But that connection between the black hole and the jet is actually really hard for us to see in detail in our observations. And so you've actually identified one of the next steps we'd like to make with some of these EHT observations is not just showing you cool stuff that's far away and then a whole bunch of black space and then a black hole event horizon. What we'd like to do is actually link up using different frequencies or different pieces of the puzzle to link up the black hole event horizon to the jet and see actually how that works, because we're not 100% sure how you link those things together and why in some cases you have a jet, in other cases you don't. Everybody thinks Sagittarius A star should have a jet. Very frustrating that it just doesn't do that. And all of our models think a jet should be there. And so far we haven't been able to find one. Maybe it's because it's tipped right along our line of sight or obscured or just too weak and we can't find it. But our models really tell us it should be there and we can't find it. So there's a lot of different reasons that you might have one or might not have one, but sometimes even when you think you should have one, you don't get one. So it's a good question, still working on it.
What do you expect the James Webb telescope pictures to tell you that you don't see now?
So James Webb is an infrared observatory. There's lots of dirty little secrets I didn't share with you, but turns out Sagittarius A star has another thing that's interesting. So I told you about its variability and how short time scale that variability is, something like 5 minutes to a half an hour, but it's also got much more spectacular variability. It doesn't drive a jet that we've seen so far, but it does drive these very bright flares. So it has outbursts that are way brighter than we kind of would have expected until we just observed them. We were first observed it at X-ray wavelengths in a really clear way, but also in the infrared, we can see it kind of flickers a little bit like a candle. And so these bright flares are something that the James Webb Space Telescope might offer us some insight into, to understanding using some of the different James Webb instruments, whether or not Those flares are coming from right next to the event horizon, whether they're coming from, say, sort of like an eddy in the accretion flow that's further away. And we've worked on this for a long time. The gravity instrument that I tried to show a little bit that is tracing some of those stellar orbits is also seeing these flares and maybe being able to track them as they orbit. So they get bright and also orbit the black hole. So there's quite a few different instruments that are trying to get in there and really see where those flares are coming from and see if we can explain them using magnetic fields or using other plasma properties. So James Webb will help with that. I think the other really important contribution that James Webb might make is understanding all the stars in the environment around the black hole. So it turns out that there are many different populations of stars in the central part of our galaxy, and they make a bunch of very different interesting structures around the black hole. And exactly how they're orbiting, what that stellar population looks like, and how they might be connected to the formation of the black hole. Do the stars kind of get more of the mass? You know, you're asking how they grow. Maybe the stars just all formed too quickly and ate up all that mass, and so it couldn't flow into the black hole. So this sort of interaction of the environment with the black hole is something that I think James Webb is going to offer a lot of really interesting insights. Lost track. At the back somewhere. Go for it. I don't know your name, but I see Asian Music Festival. Or maybe that's not Asian. Aspen Music Festival. That makes so much more sense. Sorry.
Okay, I have two quick questions. So, is the density of all black holes the same? Like the ratio of size to mass the same for all black holes? And also, I always thought the pictures of the black holes were pictures of radiation coming from the black holes, but actually, like I learned that just like photons being flung towards us around it. So my question is, can you observe the Hawking radiation or observe like the black hole itself?
So the two questions, just to hopefully I can paraphrase them well. The first question was, is there some fixed ratio between the radius and the mass of the black hole? So do they have a sort of a similar density from one to the next? And then the second question was, can we observe Hawking radiation near the vicinity of the event horizon? So we do have scaling relations that seem very robust between the mass of the black hole and the radius of the event horizon. I would prefer to say it that way than to say that we have a constant density, because density stops really making any sense once stuff falls into the black hole. We really don't know what happens to stuff in there. Does it all fall down to a point? What does that mean? 6.5 billion solar masses at a point. I don't know. You work on that for a career, right? Does it rebound? So density, I don't know, Jason might think something different, but we do see fairly robust fixed relations between the mass that we can measure and how big we think that event horizon is going to be in projection on the sky. And that's part of the reason we knew to go chase down these two black holes. We had some idea of what their mass might be. We knew how far away they were. That could give us an estimate of how big that event horizon, that shadow in the middle, might be, and whether we had a hope of being able to detect it. It was specifically because of that fairly well-known relationship. The second question about Hawking radiation is, maybe I'm a pessimist here. I'm usually an optimist, but I'm a pessimist on this one. Hawking radiation is, where you have a particle and an antiparticle. This is Daryl's very simple explanation, pop into existence out of the vacuum. One of those falls across the event horizon and the other one escapes. So you have to have something that's able to pick up that particle that's escaping. And there's all this other gunk, right? So astronomy is in this fix a lot, that we love being able to see stuff. Sometimes the stuff that you can see obscures something that's much fainter, even if it's there. So you're not completely sure that Hawking radiation is really a thing that happens. It's a cool idea. We can write down the equations and kind of understand what that might look like, but being able to observe it is an entirely different matter. Partly because anything we can see already has so many photons in the vicinity that it's going to wash out that signature. Jason, help me. I don't know. How about right in the middle, white, and then we'll go all the way to the back.
Does the black hole have a purpose, or is there a layman's way of explaining its impact on the galaxy?
Yeah, so we have a couple of interesting ways. So we think that black holes and galaxies, oh, sorry, the question was, does the black hole have a kind of a purpose or a central function in the context of the galaxy? Is that fair? So the way we think about this when we think back to the earliest times in the universe is that mass is slowly aggregating into big gravitating structures. And the black hole, the supermassive black hole, remember, I really haven't talked about the other class of black holes, which are the small ones that come from stellar explosions. So let's just think about the black holes that are in the centers of galaxies. We think that those galaxies, or those black holes and the galaxies they're in, co-evolve. They each start as a slightly more dense place in the universe. That slightly more dense place attracts more mass into it. As that mass grows, the galaxy grows, and alongside it, the black hole grows. So they are sort of like siblings in the same household. They grow together over cosmic time, and we see many correlations between them because of that coevolution. Sometimes when there's a jet or a wind or a shock or something explosive, you can see a direct or immediate interaction. You know, this happened in the black hole, it had a big accretion event, it sent out a big burst of energy, and it smashed into some part of the galaxy. Sometimes we can put them together one-on-one like that. But more often what we see are correlations that show us that these two entities, the galaxy and the black hole in its center, kind of grew up together. And that gives us relationships that show us things like how many stars and how fast the stars are moving in the center region of the galaxy and the mass of the black hole are very tightly correlated. So we can see a lot of components of galaxies that seem to have an intimate relationship with the black hole. It's not that the black hole makes the stars or the stars make the black hole. They really just grow up together in this kind of denser region of the universe. I think we're going all the way to the back. We could do two in the back. Sure.
The universe is three-dimensional. You were saying you couldn't always see the black holes. Is the event horizon essentially two-dimensional relative to everything, or does everything suck in from both sides?
That's a great question. So the question is this a 2D kind of visual, or is this really truly a 3D object? So it's really truly a 3D object. The black hole you can think of as being a sphere, just like our globe. And what we see are, imagine that you've got a black ball and a flashlight behind it. And that flashlight is shining on the back, but now the ball has this special property of being able to take some of the photons that are hitting the back and just twist them up over it. So that now it's not so much that the ball is two-dimensional, the ball is three-dimensional, but from your perspective, the light that is me is shining photons that are kind of headed your direction, and they get redirected a little bit by the black hole and kind of focused into your line of sight. So that's a little bit of what we're seeing. It's called gravitational lensing or focusing. But you might have that, you know, if in this case, the thing that's illuminating it is not a single directional flashlight, but a blob of gas that's all the way around it, you might imagine that you could see that same image from a lot of different perspectives because the flashlight is three-dimensional also.
Thank you. Two questions. The first one is a Roger Penrose one about time zero in black holes. And what happens?
Probably not know the answer, but go.
No, I mean, what happens to time zero in a black hole? I saw Penrose up there and I figured that was probably something. And the second one is about the artificial intelligence and machine learning and stuff and how that's going to shape the future of your research.
Yeah, great. Okay, so the first question was about Roger Penrose and time zero, and the second question was about AI and machine learning, artificial intelligence machine learning. So I don't know much about Roger Penrose and time zero. I imagine that you're imagining that point kind of down at the very center of the black hole. So my brother is a theoretical physicist. I am an observational theorist. Physicist, sorry, not theorist, non-theorist observer. So I look at the universe and I try to observe things that are there. Chris and Jason and a few other people in here are on the theory side and could probably do a better job of that. But I can tell you one just very exotic, cool, fun thing that my brother studies. And that is that maybe that mass gets down to the Planck scale, which is what we think may be some sort of fundamental size scale, and actually rebounds off that scale. The mass can't be compressed anymore. And then it has to come flowing back out. And so these are called white holes. It's when the stuff comes exploding back out of the black hole. The problem is it takes 10 to the 30 times the age of the universe for that to happen. So to me, I'm like, my brother, I love him very much. And I'm like, that's nice, Hal, but give me something I'm going to see in something less than 10 to the 30 times the age of the universe. So this is, he works a lot with a guy named Carlo Rovelli, who's a wonderful sort of sharer of physics and theoretical physics, and they think about these things. But yeah, so I don't know is the answer. Not sure any of us really know. I think there's a lot of really interesting stuff you can think about if you're down in that really exotic regime. The second question about AI and machine learning is really profound. In fact, I had a conversation with Chris, who's sitting in the front row here, about how many of these, just how intense this data analysis really is. And we're using every tool we can throw at it. So as astrophysicists, or as an astrophysicist, I don't develop new machine learning algorithms, but some of our colleagues do. Katie Bauman is a wonderful member of our team. Andrew Chale is here. I don't know if he's in the audience, but here with us at this meeting. And these are people who think really deeply and sometimes do develop their own algorithms, but more often than not, we're applying ones that are developed for, I don't know, figuring out what you're going to buy next at Target, and using that to try to figure out what we're going to get next when we look at a black hole, right? So a lot of these algorithms are really, really useful. The tricky part about machine learning and AI is really this whole new domain that's emerging called interpretability and explainability. So I can shove something into a tool and get an answer out, but do I know what that tool was looking at? I'll give you a great example that a machine learning specialist gave me recently. They tried to train a machine learning tool to pick up to use a patient's profile to figure out how likely they were to be susceptible to COVID or to get COVID. And so they gave this entire profile, lung capacity, oxygen uptake, all these profiles. They fed into the machine learning tool, and the machine learning tool was amazing. It predicted every person in that hospital that got COVID. Turns out when they looked at what it was actually keying off of, the stage. None of the lung capacity, none of the oxygen uptake, zero of that mattered. You did not need a machine learning tool to look at the age and make a probability somebody was going to be susceptible to COVID. So these tools are amazing, but we can't just blindly throw them at things without trying to understand what they're using when they make a prediction. And so this is this whole world of explainability and interpretability. And I think it's fascinating, and I think we'll get more sophisticated, and we throw everything, including the kitchen sink, at our problems. They're so hard. We have brand new instruments like the Rubin Observatory. They're going to generate petabytes of data every day, right? It's a huge challenge for astrophysicists to be able to manipulate and learn from our data, because the data is just getting so big. Maybe we'll do like 3 more. 1, 2, 3.
Okay, so I was wondering about the pictures and how you decide, like the weight of the pictures and how to sort them, because if you sort them, you get a little bit different.
Yeah, incrementally, it would look a little bit different. If you chose, instead of, oh, sorry, there was that flyby image where I showed you the different classes of images and how they got combined, how the different things got weighted. The question was, if you made that classification just a little different, maybe you had a 5th category, maybe you only did 3 categories instead of 4, wouldn't your image look just a little bit different? And the answer is yes, it would look just a little bit different. Probably to our eyes, it really wouldn't look any different. But it is true that when you are missing data, you can only reconstruct it so perfectly. And that means that there is some uncertainty in the image. I can give you a very simple example about the Sagittarius A image. Notice how it had 3 spots? Notice how I didn't tell you those were hot things, blobs orbiting around the black hole? I would never tell you that. Anybody telling you that is lying to you. There are hot spots that orbit around the black hole. Those 3 we can show you. We don't really trust them. We're not really sure that it's hotter there. Sometimes we just have a little bit more sensitivity at the time of the night when we're able to image that side. We have a lot of different things that we're not quite certain. So I would never try to be the saleswoman that would tell you that those spots are really something you should interpret physically. We do think there are probably hot spots in that disk. Those 3, give me a few more years of data. Let me think about it a little bit more. I'll get back to you. So yeah, absolutely. You could choose a slightly different algorithm, choose a slightly different classification scheme. You would get a slightly different image, but it's not going to look hugely different than the one. Remember, I was purple shirt and then pink shirt. And I think we probably should wrap it up, and I'm happy to chat with people afterward, but I don't want people to be held hostage here.
Is it thought that every galaxy has a massive black hole at the center?
Yeah, that's a super good question. So the question is, do we think that every galaxy has a supermassive black hole in its center? And the answer is basically yes. I want to put a caveat on that, that we think that every massive galaxy has a massive black hole at its center. So we're pretty confident up at the high mass end of the galaxy spectrum. This narrative I was giving about the coevolution of galaxies and black holes really does yield a massive black hole, supermassive black hole in every massive galaxy. When we get down to the lower mass galaxies, it gets a bit more sketchy. Those ones are often not as organized dynamically. Sometimes they have kind of weird tendrils. They don't always have perfect spiral arms. And because their black holes are less massive, they're harder for us to detect. And so I would say that we become less and less certain as you move down to lower and lower mass galaxies. There's one very interesting, so I've told you that we have low mass black holes that come from exploding stars, we think mostly, or mergers of exploded stars. And we have the supermassive black holes, and there's kind of a gap in the middle. We call this the sort of region of intermediate mass black holes, and they might be the ones that live in those smaller galaxies. We have a really hard time finding them. And it's just an outstanding problem, like where are they? Especially if I'm going to build a big thing from a small thing, I should have something kind of like along the way, right? But we really have a hard time finding those black holes. And it may be because they don't successfully form in the centers of smaller galaxies. So yes, basically, but not 100% certain on the low mass end.
Is it the fate of all of the trillions of stars that they will eventually end up as some sort of small black hole, maybe larger?
Oh, that's a good question. No, but a lot of them do. So it's actually a function of mass. So the question was, do all stars end their lives as black holes? And no, but they do, many of them end their lives as some kind of what we would call a compact object. So it's a remnant. You can think of it like a charcoal briquette in space. So our sun, it turns out, doesn't have enough mass to shrink down into a black hole. So basically you have to get enough mass to shove the electron, enough gravitational force to shove the electron into the proton to make a neutron. And then you make neutron stars. And then if the neutrons are so compressed by the gravity of the object, then they can shrink down into an even smaller volume and become a black hole. But if you don't have enough mass, you might halt at a neutron star. So that's a ball of stuff that doesn't have an event horizon and is not perfectly pure neutrons, but is basically a hot briquette made of neutrons. If you have even less mass, which this is the case of our sun, you never successfully build up enough pressure to shove that electron into the proton and make a neutron. And so you sort of halt at, sort of a plasma blob that's got electrons and protons kind of fighting around in there, but basically stops and is stable. That's called a white dwarf. And that white dwarf actually really just steadily cools over time. Same with the neutron stars, they cool over time. So only the most massive stars make black holes. And the kind of more intermediate mass ones make neutron stars. And then the lower mass stars, which actually make up the majority of the stars in the universe, will end their lives as white dwarfs. And basically all three of those things occur when you run out of enough generative energy in the center of the star from fusion. So you no longer have the lighter elements that you're capable of fusing to kind of create the central engine of the star. And that's when you start to evolve toward becoming a compact object. Okay, we're gonna call it. I'm happy to chat with people after too, if you want to hang out.